All right. Hello, everybody. Welcome to Hoon Academy Lesson 6. So Lesson 6 is very much a continuation of Lesson 5. It's a very important lesson that will bring you to understanding Hoon on a structural level. And after this, 7 and 8 are going to be smooth sailing to the end. So this is really the meat and potatoes of the course. So in last lesson, we introduced a pattern called a core, and we explored the mechanics of cores. Today, we will learn that cores can evolve into all sorts of useful structures, which are just cores underneath. The bar family of runes is for making cores, and we're going to learn several different bar runes, which are all actually just bar sen cores underneath. So I don't know if you guys know Pokemon, but in Pokemon here we have a very plain looking creature, which has all these evolutions, all these different forms that it can take, but underneath it's just one of these. So, all right. So recall that in last lesson, um, we learned that cores often have a piece of data pinned to the head of the subject before they're created. This piece of data becomes a sample of the core right here. For example, in this core, the sample is the value n equals 5. So we pin n to 5. Then we use bar sen to create a core. It grabs the current subject at the time it's created, which has n equals 5 at the head, and it goes right here at the head of the right branch. So in this case, there's actually a special rune that we can use. A door is a core that has a sample pinned to the head of its payload. And you can create one with the bar cap rune. So it takes several arguments. The first argument it takes is actually a type definition. This is in structure mode, which we may recall. And then it takes several arms. So as before with bar sen, it's going to be the name for an arm and whatever Hoon code you want to put inside the arm. So what does it do with this type? Well, it's going to grab the bunt or default value of that type and then pin it to the head of the subject for the core creation. So it's going to put that as the sample for the core. Recall that we know this syntax, ket tar, let's say pat ud, that's going to grab the default value of a pat ud, which is 0. Or you can use a sugar syntax, tar pat ud, get 0, tar pat da, the date is that date, tar pat p is zod. So you guys may remember this from lesson 2. So let's use this door notation to write this core that we just went over. It's going to look like this. You guys see that in the chat? So that's it. The structure that we've created here is exactly equivalent to this structure. So bar cab n equals pat ud at the head, and then this arm is equivalent to pinning n to 0 and then using bar sen to declare a core. We can do all the same things we did with the core since there's the exact same structure underneath. So for example, we can compose our core with a call to n to see that it returns the value 0 because this made n be pinned to the value 0. We can compose this core with a call to its buck arm. Let's say grab the buck arm of this door, and it's going to give us sen.n because this default value for n, 0, is less than 10. It's not greater than 10. We can make a new copy of it with a changed value for n. We can say, let's make a new door here with n changed to 11, and we can't see the change value, but this is indeed the output of a core. We can then invoke the arm of the new core to get a yes, because 11 is bigger than 10. And we can do all this in one step with the send sig room. So here we're saying the core is the subject or the door. We're saying call its buck arm of this with a new sample 11, and we get a yes. So this is all, should look very familiar. This is just what we did maybe in the homework or at the end of last lesson, but with this door notation set of the core. So we're just showing that this is the exact same thing, different syntax. So in Hoon, the purpose of a function is fulfilled by what we call gates. So far, we've heard this term gate, and we've heard that utilities like add, mul, gth, lth, and so on are all gates. However, we haven't learned exactly what they are underneath until now. A gate is simply a door with a single arm buck. That's it. But instead of writing out the door with a door notation or with the core notation, we have another rune we can use, which is bar tis. So this is what we just wrote, and this is the exactly equivalent thing written with a bar tis. We can do all the same things that we just did with this written as a gate as we did written as a door, because it's the same thing. So we can set this as a subject, grab n from it, and see that n has a value 0 in this core. We can set it as a subject and run its buck arm. Even though there's no buck in here, we can still refer to it. And we get no, because 0 is not greater than 10. We can make a new copy of it with a changed n value. And we can change its sample value and run the buck arm to see that, yes, 11 is greater than 10. So put that code for the gate in the chat. In general, usage of bartiz looks like this. It takes two children. The first one is a spec for the sample in structure mode. And the second child is a Hoon expression that probably does something with the sample. So it probably computes something based on what the sample is. This is a wide form, and this makes a gate, which is just a door with one arm buck. So this is still a little bit unwieldy syntax for calling this gate. We can actually simplify this even further. Recall that we learned early on to use senhep to call a gate, like senhep div 8.2. Oh, sorry. Div 8.2, and you get 4, right? And we learned that the sugar syntax looks like this. We can use senhep with this gate that we just wrote right here. So we can say, let's set this gate as a subject. Then we do senhep dot for the subject, which is that gate, and then 11. Yes, 11 is bigger than 10. To make this look a bit more familiar, we can say hisfaz gth10. Let's call this thing gth10. Put the code for the gate there, and then do senhep gth10 11. Yes, 11 is bigger than 10. So this actually gives us a deeper understanding of the senhep rune than what we had before. So before we learned it as we're calling a gate with a sample, but in this, now that we have a deeper understanding of cores, we can say senhep takes a gate, which is a core with a sample and an arm buck. and a sample. It substitutes that sample in, and it calls that hidden buck arm. Does buck also work instead of dot? Do you mean in this code? Well, let's try it. Let's try it. So what's that gonna do? I think this first argument to the senhap needs to refer to a core, not an arm of a core, but let's see what happens. Yeah. So it wants a whole core here, and its senhap is going to find the buck arm within that core. If you just try to do buck here, it's going to say, hey, I'm looking for a core, not an arm. Can cores with multiple arms be invoked as gates so long as they specify a buck arm? Yeah, I think they can actually. But let's try it. That's a great question. So let's do bar cab n equals pet d. Let's make a buck arm, GTH n10. Let's make another arm. Let's call it A, and let's do GTH n20. I don't know. Then let's close that. And then let's say senhep dot the subject, the whole core, with 11. Let's see what happens. Yes. So great question, Ron. And the answer is yes. All right. And we kind of just covered this, but since gates are just cores with samples, senhep also works on things that are written with bar sen or bar buck, a bar cab, sorry, as long as they have a sample in the buck arm. So even if they have more arms, they still work. So all of these three are equivalent ways to write the same thing. So this is what we just learned. Here's what we learned with the door notation. So here we're explicitly writing out the buck arm, and here we're explicitly writing out the sample, but these are all the same structure. So we can like if you wanted to write out the whole core, pen n to tar ud, write out the arm and call senhep on it. We can do that. All right. Any questions on that so far? Okay, so if there's no questions, moving on. So now that we know what gates are underneath, we can investigate some gates in the standard library. Since a gate is a core with a sample and a single arm buck, we should be able to access these different parts. So we know that add refers to an arm in the core of the standard library. And after you build it, it's going to have these parts just like any core. So let's set add as a subject, and let's get its battery at the +2 address. Let's see what's in there. And it gets us this piece of knock code, which is actually the knock for adding two numbers. So we don't have to parse this right now, but that's what it is. The sample is going to be at the +6 address. So let's see what the sample for add is. And it's a cell of a equals 0 and b equals 0. So that tells us that add has some default values loaded in, and it's just 0, 0. And we can call the buck arm of add. This is an unorthodox way to call add, but we can call that default arm to add 0 and 0 to get 0. We can use sentis on add. We can say, let's set add as a subject. Then let's use sentis to change a in add to 10, b in add to 5, and then call the buck arm of add. And that gives us 15. So that's a much longer way to call add 1015, but this just shows you that it's core underneath. And we can do the same thing with sensig. So set add as a subject, sensig, the buck arm, we want to call the buck arm of this with the new sample 10.5. So this really shows us what exactly gates are underneath. They're just cores and how they work. Okay. Most of the time when you're writing gates, you won't need to go into these details. You just write it with the bar_tis, but it's good to understand structurally what's going on. So when you're writing gates, it's good etiquette to use ket_hep inside the gate to enforce that the output of the gate should be a certain type. It helps you know the gate's working correctly, and it helps you catch bugs before the gate is compiled. So, for example, in our GTH10 gate, we could do this. This is the same as before. This is a new line we add. We're just saying ket_hep. We want to make sure the output of this is a type union of send.y or send.n. So we want to make sure this gives us either a send.y or send.n. And here's the code of the gate as before. So yeah, that's fine. When not using a ket_hep, how does a gate arrive at its default type? It just depends on what you put in there. So here, in this gate, I invoke the GTH gate. That gate has its own behavior, and that gate has a ket_hep inside it, which enforces that the output should be a yes or no. So actually, like, there is a ket_hep in here, but it's hidden inside this GTH. So it just depends on whatever logic is going on, really. That was an answer to Ron's question. When not using ket_hep, how does a gate arrive at its default type? All right. So, what is glob? I'm not sure what glob is. Maybe you could reformulate that. Tar pat ud. Oh yeah, so tar pat ud. So let's type it in. Tar pat ud. That's 0 because tar is the sugar syntax for ket_tar. Ket_tar pat ud gives you 0. Tar pat p gives you zar. Tar pat da gives you 2001. Yep. So suppose that you want to save a gate so you can call it like a script from the dojo. This is what's called a generator. Let's walk through creating and using a generator. So first, I'm going to bring up the VS Code. So one moment. All right. So here's how we write a generator and save it to our base desk. First, you're going to want to run bar mount send base. And this is just going to make sure that that base desk is mounted. Recall that mounted means it's also appearing on Earth, appearing on your Unix computer. Okay, so next we're going to go to open, let's do new file. Let's make a new file. And let's take our GTH10 gate, put that in here, and then let's save it in Zod base gen, the folder for generators is the gen folder, and let's save it as gth10.hoon. Okay, so it's there from a previous iteration of the class, but just right over that one. So we save this code, and then here we're going to run bar commit send base. And committing just means taking that code that you just saved on Earth and pushing it to Mars. So we show that GTH10 shows up. And now we just need to run plus GTH10, a single space, not a double space, and then 11, which is a sample to the generator, right? And now it works. So we got this gate saved as a generator and we ran it from the dojo. If you want to edit this generator, just edit the file, save it, and run commit base again. So let's change our generator to compare two numbers. Yep, a single space. And let's save this as gthab.hoon. So gonna run commit base again. And now we can run lush gthab 8, 7. Oh, sorry. So the thing you have to keep in mind, which just tripped me up, is that when you have a generator which takes a more than one thing as an argument, its sample is a noun, a cell of more than one thing, you're going to pass it in not with spaces, but you're going to pass it in a single noun like this. So 8, 7 in a cell. So that's we're passing the generator a single thing, but that single thing is a cell containing the two arguments. So now it's going to work. Hermes says, what kind of syntax is bar mount? Is there a rune behind this? So bar mount is dojo specific syntax to manipulate the dojo. It's not Hoon code. It is like running commands in the terminal, like ls, running cd change directory. It's bar mount is like commands to manipulate your Urbit computer. It's not Hoon. Yeah. Can you call gthab with senhep? No, I don't. You can't. So, well, let's try it. gthab. I don't think this is gonna work, but yeah. So, no, you can't use senhep here because this being saved as a generator is a different thing than it being in the standard subject of the dojo. So this is the syntax to call something as a generator, a file saved in the gen folder, and this is the syntax to call a gate which is in your subject. So yeah, this is not going to work in this case. Can you Darset Labrum says, can you load it into the dojo? Yes, actually, you can import this as a library that's then in your standard subject, but that's something we'll learn in lesson 7 or 8. Jesus says, yeah, oh yeah, you guys have the same question. Yeah, so yeah, you can do that, but we will learn that syntax later. Okay, so this is just the first taste of using a generator. So, all right, so if there's no more questions, we'll move on, but let me know if there's any more questions. Okay, so recall that in last lesson, we learned that we can have cores where the arms of the cores contain code for other cores. So of course this means we can have gates. We can have gates in the arms of cores as well, since gates are cores, right? So let's take a look at this code right here. This is a core, and its double arm contains a gate. That gate takes an argument or takes a sample A, which is a number, multiplies 2 by A. Its triple arm contains a gate, which takes A and multiplies 3 by A, and its quadruple arm is a gate which takes A and multiplies 4 by A. So we can compose this core with a call to triple, and that's just going to return this gate. It's going to return that gate, which is this core looking output right here. We can also compose this with calling senhep triple on a sample of 4, and then we get 12. Does that make sense to everybody? So we have this core which contains gates. We're composing this with senhep triple, calling this, and then we get 12. This is actually the same thing that's going on when you do senhep add, senhep gth, whatever. It's just that this part of it is hidden in the Dojo subject. But when you do like senhep add 1, 2, this is the exact same thing that's going on. That's here pretty much. Okay, so we can also make this outer core into a door, and we can have the inputs to that door be used in the definitions of these inner gates. So this is called a gate building. Oops, sorry. This is called a gate building door. Oh, sorry. So let's go through an example. Hopefully we're all familiar with linear functions that looks like this, right? Y equals ax plus b. A denotes the slope of the line. B denotes where the line crosses the y-axis. Let's build a door which can represent any linear equation like this as a gate. So here's the code. Put this in the chat for you guys. Let's go over all the parts of this code in detail. So first we have a door which has a sample, which is 2 numbers. A is a PAT-UD, B is a PAT-UD. That door has a single arm, buck. This is the contents of the arm, which is a gate, bar tis. That gate takes a sample, which is a number x, is a PAT-UD x. It's used right here. We have this kethep inside, which is just saying, I want the output of my gate to be a PAT-UD. In the content of the gate, this inner gate, it also uses this A and B that was passed to it from this outer door. And with the A, B, and the X, it computes AX plus B. So let's we can use this to, we can name this core linear, and then we can do sensig. Let's call the buck arm of this door linear with the inputs 4, 2. And this is going to return a gate. This is going to return this gate inside with 4 set, A set to 4 and B set to 2. So we can't see it, but this is a gate which represents the equation 4x plus 2. If we want to use this, then we can say, oh, sorry. And this is the sugar syntax right here. If we want to use this, here's what we do. So we have this sensig, the sugar syntax. We're calling this buck arm of linear with 4, 2 to build a gate which represents 4x plus 2. Then we're going to use senhep to call this gate that we built with the input 1. So this whole thing is going to represent plugging in x equals 1 to the equation 4x plus 2. And 4 times 1 plus 2 is going to be 6, right? So there we have it. You get 6. Are there any questions on that? All right. So there's no questions. We're going to move on to the next big important part of this lesson. So let's learn how to do recursion in Hoon. Recall that in lesson 0, we studied a simple recursive function like this, right? So what's this function doing? It says it's going to take an input n. If n equals 0, then return n. Otherwise, return the function computed on n minus 1. So if we give this a 3, it's going to say, is 3 equals 0? No. So compute the function of 3 minus 1. Compute the function of 2. What is function of 2? Is 2 equals 0? No. So compute function of 2 minus 1, which is 1. What is function of 1? Does 1 equal 0? No. So compute the function of 1 minus 1, which is function of 0. And what is function of 0? 0 equals 0, so it's 0. So basically, for any number that you throw in here, any positive integer, it's just going to give you 0 back. Right? Let's understand how to code this function in here. Let's look at this piece of code and understand what's going on. Put it in the chat. Okay. So we're going to start off by pinning n to the value 3 with tisfaz. That becomes a sample of this core, which is defined next. We have a bar sen declaring a core. It's closed with this hep at the bottom. This core has a single arm buck. This whole block of code is the arm and its definition. This is the definition of the arm. First, it starts with this whatcol. Remember that whatcol means if this first child gives you a send.y, do the second child. Otherwise, do the third child. What is this? This is sugar for .tis. This is going to give you a send.y if n is equal to 0 and a send.n otherwise. So if this was a send.y, meaning n equals 0, then output n. Otherwise, do this. Otherwise, do this whole code block. And what is this doing? Recall that in last lesson, we learned that send.tis means to build something with changes made to parts of it. The first argument to this send.tis is buck, which is actually referring to this. It's the own arm that contains this code. This buck is referring to this. So recall that if send.tis is given an arm as its first argument, then it doesn't just give you back the thing with changes, but it's actually going to build the core containing it with the changes and also run that buck arm. So yeah, this is how we get recursion, is that this code in the buck arm can refer to the arm itself. So this whole piece of code is going to mean build and run this arm with n changed to n minus 1. All right. So if we just take this code and put it in the dojo, it's going to return a core because this is a definition of a core. So to kick it off, we're going to have to call this buck arm. We're going to start this recursion with a call to this buck arm. So we're going to do this tisgar in front and then the call to buck at the bottom. And we get a 0. So seems to be working as expected. Let's go through the logic of what happened when we just ran this piece of code right here. So this tisgar and this buck says run the buck arm of this stuff. You start with n set to 3. We're going to ask, does 3 equal 0? No. So do this. What is this? This is saying build this whole core again and run the buck arm with n set to 3 minus 1 equals 2. So here we are again, back at this buck arm, but now n is equal to 2. Does 2 equal 0? No. So do this. Rebuild this core and run its buck arm with n set to 2 minus 1 equals 1. Here we are again with n equals 1. Does 1 equal 0? No. So do this. Rebuild the core and run the buck arm with n equals 1 minus 1 equals 0. Here we are again with n equals 0. Does 0 equal 0? Yes. So return n equals 0. Any questions on that? Can we still do this with bar tis? Actually, yes. Yes. You're very much ahead of the lesson. That's going to be one of the questions on the homework. But yes, you can do it with any core that has a buck arm. So if you have a core with a single arm buck, the Urbit term for this is a trap. And there's a rune you can use to write this faster, which is bar dot. The rune works like this. It just takes a single child, a Hoon expression, and it puts it as the single buck arm of a core. So we could have written our above code a little more shortly. Instead of doing this bar sen, less buck, all this stuff, we can just replace that whole thing with a bar dot. Let's run this code and make sure it does the same thing with the bar dot. And we get a 0 out of it. So we just change this room. If you have a core with a single arm buck, and you also immediately call and run that arm, then you can write it even more shortly with the rune bar hep. This is called building a trap and kicking it. And bar hep is going to be the rune you'll use most often for writing recursion in Hoon. Yes, Franklin, bar dot gives you implicit buck. Is bar sen the only rune that doesn't assume a single buck arm? No, bar cab as well. Bar cab as well doesn't assume a single buck arm. Yeah, so bar hep is going to make a core with a single buck arm and immediately run that arm. So we can write the above code again shorter by replacing this bar dot with this call to the buck arm with just this bar hep. So let's run it now. Make sure it does the same thing. Put this code in the chat. So tisfaz n3 bar hep, and then this logic is all the same. And that's it. You get the 0. So this bar hep is running that arm immediately without needing to compose it with a call to it. So we've already greatly shortened this recursive code. We can even shorten it one more time by replacing this sentis with a sugar syntax. So we can, instead of this sentis, buck, and so on, we can use this sugar syntax that we learned in last lesson, which is just the thing you're changing on the outside of these parentheses, and we're changing n to sub n1. So make sure that works still. So get a 0 out. So what happens if we do something weird? This tisfaz n3 was outside of this trap. And what if we put it inside? What if we put it inside here? Would this mean that every time we recurse into here, n is gonna get reset to 3, and then maybe this will go into an infinite loop? Well, let's see what happens. Let's see what happens. I'll put this code in the chat too. So it actually did an infinite loop, but it gave you an error message, tac.n find.n. So what does that mean? So here we have written this code in two equivalent ways. This is the original long piece of code, and this is with all the compressions that we've done, right? And recall that this bold apart means rebuild this core with n changed to n-1, and then run the buck arm. But what's going on here? This CentIs actually can't find an n to change here. And that's why we get this error tac.n find.n. And that's because what's going on is data that's in the arm of a core is unbuilt code. It's so this n actually doesn't exist when this is trying to look for it. And we'll see that in this diagram here. So when this TISFAS is on the inside of this bar hep, it's in the buck arm. So it's going to end up in this left branch in the battery of the core. And when you invoke this arm to call the CentIs, it's going to look over here for an n, and it's going to say, hey, I can't find an n. Or it's going to look in this whole thing, but because this TISFAS N3 is inside this buck arm, it doesn't exist yet. So it can't find this n. Whereas if we put it out here, it's going to be in the payload. That n is going to exist here at the head of the payload, and it's going to find this n. Any questions on that? So you'd think this tries to make an infinite loop, but it actually makes it have a more interesting error. Okay, so if there's no questions, we'll move on. Let's write a trap to actually do something more useful than just counting down to 0. So let's write a trap that can add up all the numbers from 1 up to whatever input number you give it. So let's look at this piece of code, drop it in the chat. So we're going to start with n set to 5 and total set to 0. We have this bar hep. We're going to ask, is n equal to 0? No. So do this branch of the code. So we're going to say the cent is going to say rebuild this core and run this hidden buck arm. Remember, this buck arm is still in here, but it's just obscured by this bar hep. With n change to 5 minus 1 equals 4, total change to 0 plus 5 equals 5. Now we're going to return here again, but now n is 4 and total is 5. We're going to ask, is 4 equal 0? No. So we're going to take this branch of the code again. This branch says rebuild this core and run the hidden buck arm with the n changed to 4 minus 1 equals 3, and total changed to 5 plus 4 equals 9, and so on and so forth. So let's run this code. Oops, sorry. Got a spacing issue. So let's run this code. Same code with n set to 5. And oh, I'm sorry. There we go. Got to rename the variable. And we get 15. Okay. We get 15 because 5 plus 4 plus 3 plus 2 plus 1, all added up is 15. So there's actually something useful we can learn to shorten this code even further. This is called natural recursion, and we can get rid of the total variable by putting the recursive call inside of a gate call to the gate add. So let's take a look at this piece of code. This is doing the same thing, but it's doing it in a perhaps more efficient way. So here we're pinning n to 5 again. They're doing this bar hep. We're saying, does n equal 0? If so, return n. Otherwise, add n to the result of the recursive call on n minus 1. So this bar means add n, and this is the recursive call to n minus 1. So in our case, this means, does n equal 0? If so, return n. Otherwise, return the result of adding 5 to the result of 4 plus 3 plus 2 plus 1. Does that make sense to everybody? So we really shortened our recursion down. So we can take this code and put it inside of a gate to give us the ability to give custom inputs to this. So let's pull up the VS Code again. Let's take this and let's save it as add nums.hoon in Zod base gen. Go over here, run commit base, save our code to Mars. And now we can do plus add nums 5, and we get 15, or we can do 100. And remember that dot is actually the comma that you'd be used to. Cool. So hopefully this code makes sense to everybody. If not, it'll be in the notes. So very, very elegant way to do this recursion. Before we end the lesson, let's cover one last example of recursion. So it's very common to use recursion to work over lists. Remember, we learned about lists in lesson 4, that they're like these cells of cells, null terminated tuple structures, right? So we can use a trap to iterate over the list and perform some action. Let's use a trap to add up all the numbers in a list of numbers. Okay, so I have this piece of code. Dropped it in the chat. So let's analyze this, see what's going on. So first, we're going to pin numList to a list of the numbers 2135 to 849. And we're going to pin total to 0. This bar hep represents a core with a single arm buck. That's what it's obscuring. And it tells you to run that buck arm immediately. This what sig is, remember we learned this in lesson 3. This is saying if my first child is sig, then do the second child, otherwise do the third child. In this case, since it's a list, this is saying if this list is the empty list, then return the total. Otherwise, do this stuff right here. What is this stuff saying? It's saying CentIs rebuild this core and run this buck arm of the core that's hidden with these changes made. And what are the changes we're doing? So here we have this i.numList and t.numList. Recall that something and t dot something refer to the head and tail of the list. And we can use these because this what sig earlier proved to the compiler that in this branch, the list is not empty and it has these faces attached. I.numList, the head of the list, is just the number 21. And t.numList is also a list. It's the list 35 to 849. So it's the remainder of the list without the head. So this is saying recurse with the head of the list added to the total and the tail of the list as the remaining list that we're going to use for the recursion. All right, so let's try that piece of code. And we get 115, which is the result of adding 21 plus 35 plus 2 plus 8 plus 49. All right, so Hermes Corp says, I get an error naked generator failure. Were you trying to do the add nums generator from the example we just did? So if you want to stick around after the class, I can definitely help you debug that. So we'll take a look. Okay. So we had this piece of code. We can actually simplify this even further. So recalling our natural recursion example that we did here, we can do the same thing. Here's a simplified version of the code. So what's going on here? We're still pinning numList to a list of these numbers. We got rid of the total variable. We're making a core with a single arm and running it. We're saying if numList is the empty list, then return 0. Otherwise, add the head of numList to the result of the recursive call on the tail of numList. So in our particular case, that means add 21 to the result of adding 35 plus 2 plus 8 plus 49. So let's run this code, and boom, we get 115 just like before. And as before, we can take this code and put it into a gate and save it as a generator. So var have n equals patud, or sorry, numList equals list patud. So we're saying the sample of our generator is going to be a list of patud numbers. Let's take this code and drop it in here. This is just the recursion. And let's save this as add numlist.hoon in the gen folder of our base desk. Save that. On Mars, we're going to run bar commit send base. And now we can do less add numlist these numbers, and we just call it generator. All right. So that brings us to the end of the lesson. Today, we saw that cores are flexible and powerful enough to enable a wide variety of uses, such as functions, generating a whole class of functions, and recursion. With this lesson, you've gone through the meat and potatoes of Hoon Academy, and you're on your way to having a good structural understanding of the whole language. In lessons 7 and 8, we're going to wrap up the course by exploring the standard library and showing you how to build production-grade code. So I have a feedback form here. I will end the recording, and I will take questions, including I can help Hermes with getting that generator working. All right. So let me end the recording. Thank you, everybody.